Okay, hello everyone. Today who's gonna do the introduction is Cornelia Hoffman because she knows our speaker really, really, really well. So Cornelia, go ahead.
Thank you, Carla, for the handover, and welcome also from my side to today's Atto Friday. I'm very happy to introduce one of my advisors during my PhD time, Dr. Alexandra Landsman. She received her PhD in 2005 from Princeton University and worked as a Marie Curie senior scientist at ETH Zurich before moving on to the Max Planck Institute for the Physics of Complex Systems in Dresden as a group leader. In 2019, she moved her group to the Ohio State University, where she is based now, and took on an associate professorship. Her group studies the ensuing dynamics when ultra-short light shines on atoms, molecules, and condensed matter systems. And the ultimate goal in this is to accurately image and control of electron dynamics on the attosecond timescale. And to this end, they use a variety of numerical and analytical methods, which I'm sure we will get some examples in the upcoming talk, ranging from solutions of Schrödinger equation to classical and semi-classical approaches to techniques from nonlinear dynamics systems. With this, I would just like to say to all the attendees, please feel free to post all of your questions in the Q&A box at any time during the talk, or if you want to ask your questions in person, raise your hand at the end of the presentation. And with that, the floor is yours, Sasha. Please take it away.
All right, so thank you for coming. I am talking about photoemission delays in molecules, which has become kind of a very popular topic in the last few years. So first, let me acknowledge my collaborators. I will in particular focus on a couple of different experimental papers. So the first one involves ionization of CO, and that was done in collaboration with the experimental group of Ursula Keller at ETH Zurich and the experimentalists in her group, whom a lot of them I know quite well because I was embedded in Ursi's group for a few years. And the second work is on a polyatomic molecule, and that was done in collaboration with a group of Matthias Kling. I also want to acknowledge my theoretical collaborators at the Max Planck Institute for the Physics of Complex Systems, where I was a group leader up until a couple of years ago. So a big driver behind the semiclassical theory that I will be discussing today is Thomas Thomas Zimmermann. He really, was kind of the driving force in the simulations, and he was also helped quite a bit by Lisa and Cornelia and Liang Wen were involved as well at the time they were at the institute. So some of the other theory, which is in the two experimental papers, was done by different people in different groups, and I have listed their names as well. So just to kind of give you a broad overview, I will give a quick background behind attosecond streaking experiments. Most of you are probably already familiar with this background because I've noticed you already had a few speakers who talked about it and are well-known experts on the topic. Then I will introduce the specific theory, the semiclassical theory, which we called classical Wigner propagation. And this theory was really instrumental in interpreting the two experiments I will talk about today. So then I will focus kind of on the specific application of this theory to polyatomic molecules done in collaboration with Matthias Kling and how it was used to probe molecular environment following ionization, and then on the experiment of diatomic CO and what ionization delays can tell us about the localization of the electron wave packet immediately following ionization. So the pump probe experiments they're either streaking or rabbit experiments. So here is a picture of a streaking experiment, and it combines an attosecond pulse, typically in the XUV. So more recently, with the advent of X-FELs and attosecond X-ray pulses, those pulses can also be in the X-ray regime. But typically using tabletop high harmonic generation, attosecond pulses are in the XUV. And they're combined with a few cycle infrared pulse. So the XUV pulse produced with tabletop high harmonic generation is typically quite weak and leads to single photon absorption. And its energy is the energy of an XUV is comparable to the ionization potential of a valence orbital in an atom or a molecule. And the infrared pulse is acting as a probe. In particular, it is not strong enough to ionize by itself because the frequency, the photon frequency is too low. But it leaves an imprint or a phase on the departing electron, which encodes timing information. So one example of such a streaking experiment is this experiment by the group of Martin Schultz, published in Nature Physics in 2017, and it involved the ionization of helium. So the bright upper trace you see is direct ionization, and the weaker trace you see is the ionization from the shake-up channel. So the basic idea is that you have an electron and it absorbs a photon and it's directly ionized into the continuum, or in the process of absorption, it can also excite a second electron into an excited state. And so then the final continuum energy of the first electron is going to be smaller, and this will lead to this second weaker trace, which is due to the shake-up channel. And of course, it tells us something about electron-electron correlation in helium, because here you have interaction of two different electrons. So the time delay is extracted from the relative shift between the two streaking traces. Experimentally, the time delay always has to be extracted relative to a different, either a different state within a single atom, or an entirely different atomic species are used. So in the case of helium, in this experiment, the time delay is extracted between a direct and a shake-up channel. And what is actually experimentally measured is called the streaking delay, which contains something you're probably all familiar with called Wigner time, or sometimes called Eisenbach-Wigner-Smith time. And this additional term, which is basically measurement induced, it's called Coulomb laser coupling. And it's fairly universal or independent of the atomic or molecular potential. So to get information about intrinsic ionization delay, one typically wants to get to this Wigner time and subtract out this Coulomb laser coupling time. So the depiction here taken from the Asiander paper is just a visual of what I already said. You have this direct ionization channel from the 1s orbital of helium, or you can have a situation where the two electrons share the energy of a single photon between them. So the Wigner time was developed in this very beautiful and simple paper published by Wigner in 1955, where he identified the delay with basically a scattering problem. So the insight is that single photon ionization is basically half scattering, and it corresponds to the shift in the peak of the outgoing wave packet due to a potential. It is defined by this equation here, where you take a partial derivative of the scattering phase with respect to energy to get the Wigner delays. And those delays really tell you something about the intrinsic dynamics of the ionization process. For instance, they go up with increasing angular momentum, as you can see in this figure on the right. But they also tell you something about the intrinsic excitation process, such as the shape resonance. So for instance, as was shown by the group of Hans Jacob at TTH, you have significant increases in delay up to 100 or so attoseconds in the presence of a shape resonance, where the electron wave packet is temporarily trapped in the potential well. So this interest in single photon ionization delays really started about 10 years ago with an experiment by the group of Martin Schultz. And this group first extracted the relative delay between a 2s and a 2p orbital in neon. A lot of you guys are probably familiar with this experiment. At the time, the delay they measured was about 20 attoseconds, which started this big theoretical controversy about what the delay actually should be. And most of the theory, including the time-dependent Schrödinger equation, seem to indicate that it should be 10 attoseconds instead of 20 attoseconds. In general, I think it's really complementary to the field when people are arguing over 10 attoseconds. I mean, it really shows how good the precision is. But in any case, so this work 10 years ago really got a lot of people interested in single photon ionization delays. And really, the most interesting thing you can apply it to is a molecule, because there is a lot that we don't know about molecules, and it would be nice to use this new tool to understand them better. But the study of molecules only started a few years ago, and the reason for that is it's actually really difficult to interpret ionization delays in molecules, both on theoretical and experimental side. So on the experimental side, the spectrum is actually very congested. So the energy levels in atoms are much better separated. In a molecule, if you look at valence orbitals, you can have like 15 valence orbitals all within a few electron volts, or all within the bandwidth of the XUV attosecond pulse. And so it's really hard to assign the electrons that you measure at the detector to which orbitals they came from. So the interpretation is quite difficult. On the theoretical side, of course, you have to model all of those ionization channels, which is also not easy. You cannot take advantage of spherical symmetry like you can in atoms. And you also cannot use the dipole approximation, where you cannot use the dipole transition rules, because you have contribution from many partial wave channels, and the orientation also becomes quite important. So what is the orientation of the molecular bond axis with respect to the XUV? So you can see that the modeling is actually, and interpretation is actually quite a bit more complicated. So despite all of those difficulties, about 5 years ago, the group of Hans Jacob at ETH made one of the first contributions to ionization delays in molecules. They used to measure ionization delays around the shape resonance in N2O, and they did in fact found significant delays due to a shape resonance, which is again when the electron wave packet gets transiently trapped, essentially because wavelengths of the electron wave function roughly fits into the potential well, which is due to the combination of the 1/r potential in case of an atom plus the angular momentum, which creates a centrifugal barrier. Okay, so I'm going to talk today then about a couple of recent experiments that I was involved in, one in a diatomic molecule, and it's a rabbit experiment. The second experiment is a streaking experiment in a polyatomic molecule known as acyl iodide. And I will also discuss the particular series that we used to interpret those two experiments. So first, let me introduce the theory. It is really a semi-classical model where the ionization step is treated quantum mechanically, and the propagation step is treated classically. So in that sense, it's reminiscent of the strong field approximation, where the ionization step is treated quantum mechanically using strong field approximation, and after that we use Monte Carlo classical simulations to understand something about the long-range potential. In this case, the theory is different because the nature of the ionization dynamics are different. It's single photon ionization. So we start with a Hamiltonian where H naught is the electronic Hamiltonian of the atom or a molecule. HXUV is part of the Hamiltonian due to the ionizing at the second XUV pulse, and the HIR is a Hamiltonian interaction with the infrared pulse. We solve the first step, the single photon ionization with the XUV within first order perturbation theory, because here we have single photon absorption. And so in this case, the total wave function can be written in the following form, as you see at the bottom of the page. So in particular, here you have initially a ground state wave function propagated in time, then it interacts with the XUV pulse. And the assumption here is that the subsequent propagation after the ionization with the XUV pulse is just some electronic Hamiltonian of the molecule plus the infrared pulse. So immediately after ionization, the XUV pulse is so weak that it does not influence the dynamics, and the dynamics are primarily driven by the unperturbed atomic or molecular potential combined with the infrared pulse. So then the ionized part of the wave function is described right here, and in particular, each new contribution at time t prime is given by this equation here. So in analogy to what we do in strong field approximation, one can then get the photoelectron spectrum, which is directly comparable with experiment by projecting this onto the momenta basis. And this is exactly what experimentalists extract. They extract final electron momenta at the detector. So in this way, the theoretical calculation can directly be compared with the experimental measurement. That's actually one advantage of this theory. There are some other theories which directly extract Wigner time, so it can be complementary to such theories. But I think it's nice to be able to directly compare calculation to experimental data. So the key is, so far the problem is quantum. But what makes it classical is that we transform the propagation step. We use the Wigner transform and apply it to the ionized wave function to obtain the initial conditions for classical propagation. So as you can see here, this is the definition of a Wigner transform, and it gives us the phase space distribution. So it gives us both the position and momentum from which we can go on and do classical propagation, where we fully can include the combined field of the parent atom or molecule and the streaking infrared field. So this Wigner it's called the quasi-probability distribution as opposed to probability distribution. And the reason for that is because it can actually become negative. So you can see here in the plot, this is a Wigner function of the XeV excited hydrogen 1s orbital. And you can see that it takes on negative as well as positive values, which is why it's a quasi-probability distribution and not a probability distribution. This is actually good because it can allow us to account for some features of the interference because the two trajectories, the negative sign can interfere with a positive sign trajectory, and that way you can include some interference as well. Even if you do purely classical propagation, you just give a negative weight to some of the trajectories. So you can actually, if you're not doing a purely classical propagation, if you're using a Moyal equation, which is shown in this extension here, this is actually equivalent to the solution of the Schrödinger equation for pure states. So in this way, dynamics can actually be exact. Nevertheless, it would be extremely complicated computationally to take account of higher order terms. So in the series that we're using, we're neglecting the third and higher order derivatives. We are only taking those two terms. And this is actually equivalent to classical propagation. So here I kind of gave you a basic outline of the semiclassical theory, which can be used to create streaking traces, which we called classical Wigner propagation method. So when we do simulations, we can also know the absolute streaking delay, unlike in the experiment, because we know exactly the phase of the laser fields that we're using. So this is a comparison at the bottom of the page. You have a comparison for hydrogen of a time-dependent Schrödinger equation and the classical Wigner propagation method. Of course, we use the same extraction procedure. And you can see, at least visually, the results are pretty similar. If we plot the delays, they're very close as well. The CWP method can be made less grainy by taking more trajectories in the Monte Carlo classical trajectory simulations. So what we used here for hydrogen is we used the Hartree-Fock approximation. One can take account, can get more sophisticated and take account of some electron-electron correlation using Dyson orbitals. Which is a pretty common approach, and that's basically can be sort of as an overlap between the atomic wave function and the ionic wave function. And one can get Dyson orbitals using computational chemistry software such as GAMES. So in this case, one can use this approach combined with Dyson orbitals to actually take account of electron correlations, such as the one seen in this Martin-Scholz experiment. In particular, one can that way also get this shake-up ionization channel in addition to the direct channel. So this is what we did here using this CWP method. As a plot here of this computation looks a little bit different from the experiment, but that's actually because we used a slightly different poles. If we extract some streaking delays between those two traces, I didn't plot them here, but there is a paper in the archive you can check out which does that. But if we do that, we actually get something pretty close to what was observed in this experimental paper. So again, this is to demonstrate that this method can even be used to take account of some electron correlations, such as shake-up channels, because I know a lot of people are interested in electron correlation. So now I will talk about kind of starting with the experiment done by Matthias Kling first, which involves polyatomic molecules, and in particular how such experiments can be used to probe the molecular environment. So one nice thing about this experiment is I talked quite a bit about how difficult it is to distinguish different ionization channels. In this case, the ionization comes from a giant resonance, so you know exactly what ionization channel it comes from. So I will get into that in a minute. But so this experiment uses photons of energy, let's say between 80 and 100 and plus EV, XUV attosecond pulse, which is around the giant dipole resonance of iodine. So the thing about the giant dipole resonance is that it is specific to a particular atom because it's an ionization of an inner core electron. So if this atom, iodine, is attached to a larger molecule, that doesn't actually change the nature of the ionization step. Because the electron is inner core, it doesn't really see the molecular environment. And this is also evidenced by the cross sections. So if you look at the cross sections plot, which is shown here, it is cross sections for different iodine containing molecules which were extracted experimentally. And you can see here that experimentally they use 3 different iodine containing molecules, and they all have approximately the same ionization cross sections. They all have this giant resonance around 100 EV. And the sort of yellow, sorry, not yellow, but kind of pinkish background is a time-dependent LDA calculations done for just iodine atom. And so you can really see that this resonance is just due to the ionization of the iodine atom. And the giant resonance is coming from a 4D shell in iodine, and there is also some electron correlation effects which lead to it being a giant resonance around 100 EV. So this was the experiment done by the group of Matthias Kling, published in this Nature Physics paper from a year ago. It involves ionization with an XUV and NIR pulse. So the important points to keep in mind about this experiment is, as I mentioned, because the ionization step is very similar in iodine atom and in any iodine containing molecule around a giant resonance, you really can just imagine the electron, the ionized electron, appearing localized around an iodine atom. So you know the starting point, and then you can really use the difference in delays between just ionization of iodine and an ionization of acyl iodide, in this case, to probe the role of the molecular environment and delays. So in this case, what role does the acyl group have on the departing electron wave packet? One nice simplifying idea is you know directly the ionization channel, and number 2, you know that the electron is localized around iodine. So any differences in delays that you see between iodine containing molecules tell us something about the role of the molecular environment. So in this case, the acyl group is actually, this group here is nearly neutral, but we still found some significant delays, which I actually find quite interesting. So the molecular environment does significantly affect dynamics of the departing electron, even if it's, you know, having close to 0 charge. Here you can see the actual experimental data. So the reference point here is neon gas, because as I mentioned, you always need a reference point in experiment. So the delay is extracted as a shift between the neon trace and the SL iodide trace. But the neon delays are fairly well understood, so we can just subtract them out of the experimental data to get the streaking delay. So the streaking delay here is Wigner time combined with a Coulomb laser coupling, which we can also subtract out, and it will be different for neon and SL iodide, as you can see in the inset, because the final electrons coming from SL iodide and from neon are at different final energies, and of course the Coulomb laser coupling term depends on the energy of the electron. So here you see experimental data. You see there is fairly large error bars at around 80 eV. That's because it's actually really difficult to get good experimental statistics at such low energy. And here you see the two curves that you see with error bars are using this Wigner classical propagation method that I explained. There are two different curves because one uses Hartree Fock and one uses CIS, this Dyson orbitals. But you can see that the two curves are pretty close to each other, which suggests that electron correlation at that level of description actually does not play a large effect. So we can just go with the Hartree Fock approximation in this case. So if we go ahead and we subtract this Coulomb laser coupling term and really just extract the pure Wigner delay, which is what people are typically interested in, we still observe an additional delay relative to pure iodine. So this additional delay is really due to the presence of an attached near neutral alkyl group, because again, in all cases, the electron wave, the ionized electron wave function is centered around the iodine atom. So ionization from iodine atoms serves as a reference point to see the impact of the rest of the molecule on this delay. So one thing is we would expect higher delays if we used more electronegative atoms, so that the attached group is not neutral, but this is something that remains to be experimentally tested. We did simulate delays for different iodine-containing molecules, and we do see significantly higher delays for some of them. Another interesting thing we see is that the orientation dependence of SL iodide delays is fairly flat. Now, the experiment itself could not resolve orientation in this case. It was all averaged over different angles, but of course in the simulation we can actually look at orientation dependent delays. And what's interesting is that for some of those molecules there is actually a significant orientation dependence to delays, which would be quite interesting to explore experimentally. So this is what the next paper I will talk about focuses. It actually is orientation dependent delays in a diatomic molecule. And one interesting point is that you can actually use this, they call it Stereo-Wigner time delay, to localize the electron wave packet following ionization. So I will discuss that here. So this is a rabbit experiment performed by the Keller group. So I think you've seen this description in prior talks. In this case, the delay is extracted by the phase shifts in the rabbit experiment. So you have an XUV pulse, which it's a 2-photon interference experiment where you have an XUV plus an infrared photon. So of particular interest here is this phi XUV is due to Atto chirp. Of particular interest is phi molecule, which encodes in it the Wigner delay and something known as the continuum delay, which is really similar to the Coulomb laser couplings that you see in streaking experiments. So the Wigner delay is defined as a partial derivative of this molecule-specific phase shift with respect to energy. So in this case, because they can resolve the delays from the carbon electron emitted from the carbon side relative to the electron emitted from the oxygen side, they can directly look at the shift in the two streaking traces. And so you don't actually need a reference in this case because you're subtracting the two streaking traces, so they serve as a reference to each other. And what's also really useful in this case is you don't have to worry about the Atto chirp and the continuum term because they're also subtracted when you take the difference between the time delay of the electron emitted from carbon minus the time delay of the electron emitted from oxygen. Those delays, they are independent of direction and they cancel each other out. So it's actually a cleaner experiment in that sense because you don't have to calculate those delays or, try to figure out what they are and worry about your Atto chirp and stuff like that. So in this case, the Stereo-Wigner time is then defined as the phase shift for electron emission from the carbon side minus the phase shift for electron emission from the oxygen side divided by twice the infrared frequency. And this is equivalent to the Wigner delay that the electron emitted from the carbon side experiences minus the Wigner delay of the electron coming from the oxygen side. So how can they really figure out the orientation? So the molecule is not oriented before the experiment, but the experiment is done in cold-terms. So based on the dissociated ionic fragments or kinetic energy release fragments in cold-terms, the Keller group was able to figure out the orientation of the molecule at the time of ionization. So in this case, I mentioned that one of the big complications of interpreting molecular ionization is conjuncted spectra. So we didn't have this issue in the last experiment in SL iodide because we were probing the giant resonance of a 4D shell in iodine. But in case of CO, we are ionizing from one of the many valence states. And so it was a bit of a challenge to figure out all the different channels which contribute to ionization. So for this case, Thomas did some 1D non-adiabatic dynamics simulations to figure out which channels contributed the most to the measurement, and using that information combined with ionization cross-sections, one can estimate the rabbit sideband contributions. So then we go on, excuse me. Okay, so the experimentalists then were able to measure the Stereo-Wigner delay in the perpendicular orientation. They had two different rabbit traces, one for parallel orientation, one for the perpendicular orientation. And for the perpendicular orientation, you would expect those delays to be bouncing around zero due to symmetry. And indeed, this is approximately what the experimentalists see. For the parallel orientation, they did observe some very negative delays at low electron energies. So you can see the delay around 5 electron volts is more than 150 attoseconds. So as I mentioned, numerically, this was quite a difficult thing to model because a lot of different states could have contributed to those delays. Based on non-adiabatic dynamic simulations, we saw that the main states contributing at lower energies are those 4 sigma states, and the main states contributing at higher energy are the 3 sigma states. So the CWP calculations, classical Wigner propagation calculations, average over different state contributions. In addition, we had simulations from Sergei Pachovsky, which were kind of ab initio TDSE simulations, and those simulations were just done for specific states like 4 sigma and 3 sigma. So to kind of understand better what happens physically, we looked at the initial conditions immediately following ionization. So one can do that using this Wigner transform, because as I mentioned, you calculate the excited electron wave packet, and then you use the Wigner transform to obtain the initial position in phase space. So the initial position and momentum from which you can do classical propagation. So this is the initial conditions for different electronic states along the molecular bond. So Q is the distance along the molecular bond. Q equal to 0 means that you're exactly midpoint between C and O. And so you can see that the localization of the electron wave packet actually changes quite a bit depending on which electronic state is involved. So here we have a 4 sigma state, which I mentioned, we believe made the main contribution at low electron energies. And you can see that in this case, the electron wave packet is really mostly localized around the carbon atom. The d pi states, we also, based on simulations, we believe the simulations and the measurement of the final kinetic energy of the ionic fragments, we also believe that d pi states contributed in perpendicular orientation especially, and you can see that the d pi states are basically evenly localized between over the entire molecule. The 9 pi states I don't think contributed significantly in this case, but the point is that you can see that it's just an example of localization around the oxygen atoms. So it just shows you how much the electron localization can shift depending on where you're on what particular state you're ionizing from. So here, if we go ahead and we plot the mean position of the electron as a function of electron energy, so what we do is we take a plot like that and we use it to calculate the mean position of the electron following ionization, and we do it for different electron energies. We get curves like this for the mean position of the red curve at the bottom is the mean position of the 4 sigma state. Then we can calculate the mean position of the d pi state in panel B, and you can see, just as is expected, the mean position is close to 0 because the electron wave packet is evenly balanced between the 2 atoms. And the 9 pi state, you can see that the mean electron position is positive. So what is actually really interesting about that is one can go ahead, you see in this panel here, that's the y-axis is actually the Stereo-Wigner time. And as we realized, it correlates extremely well with the mean electron position. In fact, it can be described by this simple formula right here, where you have twice the initial location of the mean position of the electron divided by the final velocity of the electron as measured at the detector. So this is the mean position Qi, and this is the final electron energy as measured at the detector, and it correlates extremely well with the experimentally measured with the Stereo-Wigner time delay, which you can extract experimentally. So you can see it right here. So what's plotted in this plot, which shows the Stereo-Wigner time delay as a function of electron energy, is exactly this formula. The solid red lines are exactly this formula, which takes the mean electron position from the plot on the left and plug it into this formula, and you see those curves. And the dotted lines are really calculations using the CWP approach. So they are really, full calculations where you take the quantum steps and you do the classical propagation. So you can see that they're surprisingly very close to each other. So what it really means is that you can really just take the final calculations, the final Stereo-Wigner time delay, either from the computation, TDSC or classical Wigner propagation method, over whatever calculation you do, and you can relate it to initial electron localization at the time of ionization. So that's kind of an illustration of how using this, kind of semi-classical approach, where you can actually see the initial conditions at the start of propagation, can really shed some insight into what's going on in the experiment. So the sort of important points made here is that, of course, it's really difficult to interpret ionization delays in molecules. So I think people really should not expect like exact agreement between theory and experiment, because so many different things are involved both on the theoretical and the experimental side. So I also showed that with two examples, the delays can provide important information about the molecular environment, not accessible by other observables such as ionization cross sections, which in the case of ethyl iodide were basically the same for different molecules, but we found that the ionization delays were different and carried some information about the molecular environment. And then also in the case of a diatomic molecule, we found that Stereo-Wigner time delays can be used to localize the electron wave packet immediately following ionization. So that's my talk. And I noticed I already had a few questions during my talk.
Yeah, so thank you so much for your talk, Sasha. It was brilliant talk. Before we start with the questions, I can see there are quite a few coming. I would like to make an announcement, and we have currently a special issue of European Physical Journal D, associated not only with the conference we had last year, Quantum Battles in Atto Science, but also with the present seminar series. We have been contacting all our speakers. If you would like to contribute, the editors are being quite flexible. Just drop us an email and let us know when you would be able to submit. It can be a tentative date that is fully okay, because the issue is growing strong, but it was very much disrupted by the pandemic. It happens, I think, whose life wasn't disrupted by the pandemic? So do let us know. They are very receptive, and if it's not, let's say, 1 year from now, if it's a few months from now, towards the end of the year is still fine, but we would love to hear from you and to have some tentative dates. So we're going to start with the questions. We have 3. So the first one is from Heina Donna. How do you do the rotational averaging? Does the CLC depend on the electron molecule angle?
Yeah, so of course there has been work showing that CLC, so you mean in case of a polyatomic molecule. Yeah, so there is some dependence of CLC on the angle. So in this case, because we were doing those semi-classical simulations, we included the infrared field in the propagation. So we took account of the CLC by the fact that we were propagating in the infrared laser field. So the averaging was done, I believe, over 12 different molecular orientations in the case of collaboration with Matthias Kling. So yes, we did the average over all the angles, and that included the CLC delay just because it was included in the propagation. The simulation was directly comparable to experiment.
So he also would like to know about the CO experiment and the interpretation. You say that C doesn't depend on the molecular angle, and have you checked this? I don't see any angle, any reason why this should be true.
Yeah, so again, yeah, CC does depend on the direction of emission. I mean, I believe there has been some work which studied that. In this case, perhaps I made a stronger statement than I meant to make. I meant we are only looking at the direction of emission along the molecular bond. So we are subtracting the direction of emission, like at 0 degrees minus 180 degrees, basically, because the measurement is, around the cone along the molecular bond. So in this case, it mostly should cancel out.
And a third question is, why do you need the classical propagation step for the CO case? Doesn't the perturbation theory for the first step give you the phase directly for each energy? Thus, couldn't you directly get the Wigner or the Wigner time directly from perturbation theory?
Yeah, so this is another theoretical approach. So for instance, in our work with Matthias, we also had the group of Hans Jacob, which used quantitative scattering theory. And in this case, it is exactly as you suggest. You get the phase of the dipole transition element, and that directly gives you the Wigner delay. So the reason we use this classical Wigner propagation, I mean, there are a number of sort of complementary advantages. One is that it is directly comparable with experimental data. So it includes all of those things like CLC, Coulomb laser coupling, and stuff like that. And another one is it gives you the initial conditions of the electron wave packet immediately following ionization. So when you do a Wigner transform, it gives you the initial conditions. And in the case of a CO experiment, for example, it was really instrumental to come up with this simple equation, which gives you electron localization following ionization just from the Stereo-Wigner time delay, which you can access experimentally.
Okay, Harnett, are you okay, or would you like to pursue the issue further and ask more questions? I think he's not. Thank you. That's absolutely fine. And we also have something from Francois Moguer. in the CWP simulations, how do we include the interaction from the atom and molecules, electrons onto the outgoing electron propagation?
Yeah, so we can include, in case of a molecule, we can include the molecular potential. So that can be done in a number of different ways. One way could be, to do an expansion about the center of the molecular bond and include the higher order terms in that expansion. But more generally, we just get the molecular potential following ionization and includes that in the propagation. In the classical propagation.
Is that fine by you? Would you like to ask further? Do feel free to unmute yourselves if you would like to inquire further.
Yes, thanks.
Okay, so we seem all fine. One thing I was curious about is when you started your talk, you said you were using Wigner quasi-probability distribution in conjunction with a classical propagation method, and that in some ways you could incorporate the effect of quantum interference. So first question that I have, why Wigner quasi-probability distributions? I mean, naively speaking, if one thinks, okay, I'm going for something classical, maybe we would consider a semi-distribution or something that doesn't have these problems with non-classicality. And second, how do you incorporate the quantum interference in your classical propagation subsequently?
Yeah, so the Wigner distribution, I mean, that's really building on the work of Eric Haller. And the idea is that it gives you initial conditions for classical propagation. So it gives you both position and momentum from which you can launch classical trajectories, which I think is actually makes it less ambiguous than what we do in the strong field approximation, because in the strong field approximation, we really just have the initial momentum following ionization, and then we have to assign the position. So we, for instance, assign the initial position as being at the tunnel exit, but then there becomes a debate as to what the tunnel exit should be exactly. So in this case, it's really unambiguous because it just gives you, the Wigner transform just gives you the initial position and momentum for each trajectory. But it can have a positive sign or a negative sign. But then you can just, if you have a trajectory which has a negative probability attached to it, you can still propagate that trajectory classically, but then give it a negative value at the end of the propagation. And in that sense, it can include, it includes interference because you have some positive, your final trajectory, what you, the only thing you can measure is the final momentum of the electron. So more than one trajectory can have the same final momentum, but some of those trajectories can have, positive value and some can have negative value. And so in that case, you can have interference between different trajectories because of the negative, because of the negative valued trajectories.
Thank you. But I mean, it was also in the spirit, the question was also in the spirit, okay, we always choose our quasi-probability functions or the quantum quasi-probability functions depending on what we want to see. So say, if you want to do something classical, why not go, for instance, for the Husimi one? Why Wigner?
Well, Wigner is one of the standard approaches. It's a prescription for obtaining phase space, an ensemble of phase space trajectories, right? So it's a standard kind of well-respected prescription, which has, precedent of being successfully applied in the past, for instance, by Eric Keller. And so, I mean, and it's a rigorous method which gives you phase space distribution. So, I mean, I consider it might be complementary to some other approaches, such as the ones that you mentioned, but it's a well-justified approach, which gives a rigorous phase space distribution, which you can even propagate exactly, although it's computationally impossible. But then you take the first two terms of the Moyal expansion, and you have a rigorous justification for classical propagation as well. So why not use it?
Yes, I agree. Okay, good point. Thank you. And we have another one from Heine Donna. In your case, isn't there a shape resonance at 10 eV? Reinhard, if you would like to unmute yourself and talk to Sasha directly, please feel free to do so.
So I believe you're right. I believe there is a shape resonance at 10 eV. Experimentally, if you look at the experimental data, it doesn't really seem to correspond to any significant increases in delays. But yes, I mean, I agree with you. There does seem to be a shape resonance at 10 eV for, yes, I agree with you. I will say that I'm not sure it has such a strong effect on ionization cross sections, because I've seen some calculations of ionization cross sections at 10 eV, and it doesn't seem to be huge. But yes, I agree it's there, but I am not sure it will give big delays.
So for anybody who would like to ask questions, we're going also to have the opportunity for you to ask them off record. So if you are a bit shy and if you don't want to be all over YouTube, hanging there, we're going to stop our recording and our transmission right now. So thank you once more so much for your really nice talk. Let's thank today's speaker, Dr. Alexandra Landsman, and see you soon. Take good care of yourselves. For those who are watching across the globe on YouTube, hope to see you next week. Bye.